we will do our shear force diagram. And after we have finished our shear force diagram, we will do use area method to find our moment diagram of the entire frame. So we draw the frame. We use our 15 kip load. We go to -15. Then it goes continuous. Then we see the -25 kip, which brings it down to -10. Goes continuous all the way up to this portion. Now we have our activity from this distributive load, which goes down to -15. So they intersect over here, intersect together. Okay. Now for this portion, we have 19.13 kips, and this distributive load brings it all the way down to -30.87, and then we have the shear force at the fixed support, which is going to bring it up to 0. Thus, it's an equilibrium. Let me redraw this so that it looks good. It looks so that it looks presentable. Now this is a constant, because they derive from point loads. This one over here is linear because it derives from distributive loads, and since this one comes from a distributive load, it's linear. So this is our shear diagram. Now we use moment to obtain our, now we use area method to obtain our moment diagram. And we draw it right at the bottom. So we start off from over here from the bottom. This square, it begins to change linearly, and it goes down to 40. Now we do our portion for the triangle that was in the shear force diagram, and that becomes a parabola, a sort of parabolic change. It's a parabolic change because in the shear diagram it was linear, so for the moment it has to be parabolic. So to the power of 2. So it goes from 40 down to -45. And this is once again using the area method. Now we take this whole thing and we find do our diagram. Reaching a maximum of 68.2, it goes down to -122.4. No, our maximum was not 68.2. Our maximum was actually -122.4, and that's going to be kinked up to 0 for equilibrium. And we obtain this all from the area method. So now we have our moment diagrams. Our moment diagrams and our shear diagram.
That's it.
And that concludes problem number 1.
Deflected shape.
Oh, and our deflected shape. For our deflected shape, there's no exact science of obtaining it, so we can use something called the cable beam analogy. And we see that this is fixed, so we once again redraw our diagram. Since this is fixed over here, we know that from here is going to be straight, but we have this shape of low, so it will bring it down. And we have the cantilever, which will bring it down again. It will bring it down this way, like this. So it will be something sort of like, sort of swag like this. And then we have this, this load over here, which will deflect it a little bit this way. So we have this way, this. No. This is an estimation of our deflected shape.
Okay, we're done. Stop highlighting it like dark stuff.
You gotta get out of the way.
Yeah.
You can, if you want, you can use
That's wrong.